Imagine trying to understand a super complex concept like a quantum bit without a map. It feels abstract, right? How do we take something purely mathematical and make it visually intuitive? Well, a qubit state, which is initially described by a combination of complex numbers, is mathematically converted into two real angles, theta and phi, that precisely pinpoint its location on the surface of the Bloch sphere. This visual representation is an indispensable tool for quantum mechanics. The fundamental reason we can do this lies in how a single qubit is defined. It exists in a superposition of two basis states, often called 0 and 1. Its state is written as a linear combination of these, each with its own complex probability amplitude. Let us call these amplitudes alpha and beta. Alpha is the amplitude for the 0 state and beta is the amplitude for the 1 state. Both alpha and beta are complex numbers. A crucial constraint is that the sum of the squared magnitudes of alpha and beta must always equal 1. This is known as the normalization condition, ensuring that the qubit must be in some state when measured. Because of this normalization, and the fact that an overall or global phase factor for the entire state is physically unobservable, we effectively reduce the for real numbers within the two complex amplitudes down to just two independent real parameters. These two parameters are exactly the polar angle theta and the azimuthal angle phi that describe a point on a sphere. To actually perform this conversion, you would first express your qubit state in its standard complex amplitude form. Then, you calculate the angle theta, which is twice the arc cosine of the magnitude of alpha, the amplitude of the 0 state. The angle phi, on the other hand, is found by taking the argument or phase of beta, the amplitude of the 1 state, minus the argument or phase of alpha. It is vital to remember that these angles are relative to the standard basis and the chosen coordinate system for the Bloch sphere. This elegant transformation provides us with more than just a pretty picture. The polar angle theta directly reflects the qubit superposition between the 0 and 1 states. A theta of 0 means it is purely in the 0 state, while a theta of 180 degrees means it is purely in the 1 state. The azimuthal angle phi captures the relative phase between these basis states, which is a critical quantum property influencing interference patterns. Understanding these angles lets you intuitively grasp how quantum gates rotate and transform a qubit, turning abstract math into geometric motion. It is an insider's secret to making quantum state manipulation much clearer. So, by converting a qubit's complex state into the simple polar and azimuthal angles of the Bloch sphere, we bridge the gap between abstract quantum mathematics and intuitive spatial understanding. This powerful visualization tool not only clarifies the behavior of individual qubits but also serves as a fundamental building block for designing, analyzing, and ultimately mastering more complex quantum circuits and algorithms. It truly makes the invisible visible, empowering you to navigate the quantum realm with confidence.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.